Okay, so I'm just going through this number one from Friday, and we're using the combined gas law method. So we did P1V1 over T1 equals P2 times V2 over T2. We crossed out the pressure because it's constant. We don't need it. We're rearranging the numbers here so we can solve for V2. And if we did 323 Kelvin times 150 milliliters, took that answer and divided by 298, what answer did we get? 163. And that's our answer, okay? Now, if you pay attention 10 minutes all week in any class, pay attention to this 10 minutes. Means those cell phones in your lap so you keep peeking down at, put them away. If you're tired and your head is on your forearms, get it up. Make sure that your earbuds are out. Make sure you are listening to this, especially those of you that are not very good at solving the equations, because I'm about to make your life simple. It's the whole reason this week is set up the way it is. I wanted you guys to get some practice with the combined gas laws, using the laws, doing the equations that way, but I'm about to show you a really simple way to do this. But you got to pay attention to this. So let's take a look at number 2. So in number 2, it says the pressure in a bicycle tire is 105 psi. So that's our initial pressure, 105 psi. It's at 25 degrees Celsius. So what do we do with that? Add 273, make it Kelvin, right? So if I add 273 to 25, 298 K. You take the bicycle up to Huntington, where the temperature is negative 5 degrees Celsius. What would negative 5 be in Kelvin? 268. So that's going to be my final temperature. And then it says, what is the pressure in the tire? So what is the new pressure? It also tells me the volume is constant and the amount of gas is constant, so those are not changing. All right, so what is the temperature doing? Going up, going down, staying the same? What is it doing? It's going down. It's going from 298 to 268. That's definitely going down. Now, how are temperature and pressure related? So how are pressure and temperature related? Like if I increase the temperature of a gas in a container and it can't expand, it can't shrink, I increase the temperature, what would happen to the pressure? It would increase. So if I increase the temperature, the pressure would also increase, right? So that's called a direct relationship. So it makes sense if I cooled it, if I decrease the temperature, the pressure would go down, right? Okay, so in this case, they'll go the same way. Pressure and temperature go the same way. So if the temperature goes down, the pressure should go down. So this is what you do. You just take the variable you're solving for, what you know, which is pressure. It's 105 psi. And you're just going to take that and you're going to multiply it by a fraction. That fraction is the ratio of temperatures. I can either do 298 over 268, or I can flip it upside down and do 268 over 298. Okay, I can do either one. Now, in choosing which one to use, if I put the big number on top, it's going to make this go up. If I put the little number on top, it's going to make this go down. What do we want 105 to do? We want it to go down. We know that the pressure is going to decrease. So I'm not going to put the bigger number on top. I'm going to put the smaller number on top. And if I solve this problem, I'm going to get the answer. Okay? So however you want to do it, you could multiply 105 times 268 and divide by 298. You could divide 268 by 298 and get a decimal. Let's do that. So where's my calculator? All right, so I've got 268 divided by 298, and that comes out to be 0.89932885906. I'll just do 0.899. So really, this is the same as 105 times 0.899. And if I do 105, oh, my calculator left. If I do 105 times 0.899, there's my answer, 94.4. Is that what you guys got? Okay, so you probably did it the other way, but this is a little simpler method, isn't it? A lot less canceling stuff and getting the variable by itself and all that's all taken care of. Okay, so let's try another one. So number three said, what would be the new pressure? What would be the new pressure if 250 cubic centimeters, that's volume, right, of gas at standard pressure? Okay, standard pressure. Now, I told you guys standard pressure is 1 atmosphere or 760 millimeters of mercury. Either one would work depending on the problem. That's just your standard pressure. If I don't have to use millimeters of mercury, if I can just use 1 atmosphere, I'm going to use it because 1's an easy number to deal with. So I'll put pressure 1 atmosphere. And then it says the gas is compressed. So we can compress a gas. Do you know why? Why can we compress a gas? Think about the particles in gases. What are they like? They're really spread out, aren't they? So since there's so much space between particles, we can compress them. We can bring their volume down. And it says we're doing that here. We're bringing the volume down to 150 cubic centimeters. And then it doesn't tell me anything about the temperature or the amount of gas. So I will assume those are constant and can be ignored. All right. So we're good to go. So what is the volume doing? Going up, going down, or staying the same? Going down. Now, careful here. If you decrease the volume, what should happen to the pressure? So if I'm squeezing this gas down into a smaller space, what should happen to the pressure? It should go up, right? So I drew a line between volume and pressure just so that we remember that's the one relationship, one and only relationship that is actually inverse. If one goes down, the other goes up. If one goes up, the other goes down. So if the volume is going down, that should make the pressure go up. So really this new method, we're just showing that we understand the concepts, the relationships between these variables. So again, if I start with trying to solve this here, okay, so I'm going to start with 1 atmosphere and multiply it by a fraction. Look at volume, which is what I've got both the initial and final. I can either do 250 over 150 or 150 over 250. What do I want to happen to 1 atmosphere? Do I want it to go down or up? What do I want it to do? I want it to go up. So if I want it to go up, I'm going to put the bigger number on top. I want to use this one, not this one. So I'm going to basically take 1 atmosphere times 250 over 150, and that's just going to be 250 over 150, which if I divide 250 by 150, I'll tell you this becomes 1 atmosphere times 1.67, which means it's 1.67 atmospheres. Pretty simple, huh? This is a point, by the way, I'm telling you, pay attention to these few minutes of class if you pay attention to any. But also, good opportunity if something doesn't make sense to stop me and ask me, wait a minute, why'd you do that? because that's how important this is to helping you. So don't just sit there and it's not making sense and you just let it go. Whatever. Stop me. Because I expect every single person in this classroom to be able to do these problems this way. Okay? So if there's any questions, stop me. I know this is not super exciting, but I want to explain number 4 because number 4 is slightly more complicated, but not really that much. Okay? So I'm going to erase this. All right. So standard pressure is 1 atmosphere or 760 millimeters of mercury. Standard temperature is 0 degrees Celsius, which we will change to Kelvin by adding 273, which makes 273. Okay, so that's standard temperature and pressure. Wherever I see standard temperature in these problems, I'm going to put in 273 K. Wherever I see standard pressure, I'm going to put in 1 atmosphere. Unless I'm made to put in millimeters of mercury, I would put 760. All right, so in number 4, it says, what would be the new volume? So what will be the new volume or final volume if 250 cubic centimeters of gas, so that's my volume, at 25 degrees Celsius, 25 plus 273 would be 298 K. Everybody with me so far? And 730 millimeters of pressure, so which is really 730 millimeters of mercury. All right. And then we're going to change it to standard conditions of temperature and pressure. So standard conditions of temperature and pressure. So standard temperature is 273 K, just like I wrote down here. And standard pressure is 1 atmosphere. But in this problem, I want to use 760 millimeters of mercury instead because that's what they used. Okay? So pressure, what is it doing? Going up, going down, staying the same? What is it doing? It's going up. What is the temperature doing? Going down. All right. They don't say anything about the amount of gas, so I'm going to assume that's staying the same, or do they tell us N is constant? Nope, they don't tell us N is constant, but they didn't mention it, so amount of gas must be constant. So in this one, instead of one, since I have 2 things that I know both initial and final for, I'm going to use 2 fractions instead of 1. I'm still going to start with the thing that I'm trying to find, volume, 250 cubic centimeters. So I'm going to multiply by 1 fraction to see what happens. Let's start with pressure since that's first. All right. So pressure could either be 730 over 760 or 760 over 730. Well, in order to decide which one we're going to use, we got to see what pressure should make the volume do. The pressure is going up. If the pressure is going up, what should happen with the volume? It's going down. That's a 1 relationship that's inverse. So one goes up, the other goes down, or vice versa. But they go different directions. So if the pressure is going up, then pressure should make the volume go down. Okay? So which one am I going to use? Smaller number on top or bigger number on top? Smaller number on top. So I'm going to do 730 over 760. Okay, so that took care of pressure. Now let's look at temperature. I can have 298 over 273, or I can have 273 over 298. Which one do I want to use? Okay, you think 273 on top? So the temperature is going down. If the temperature is going down, how is temperature related to volume? Directly. So if the temperature goes down, it should make the volume go down as well. So you're right. I want to put 273 on top, smaller number on top. And that's the equation right there, guys. I could change those to decimals. So 250 times 730 divided by 760 which is 0.96 or 0.961, whatever you want to use. If you use more decimals, you'll get a more accurate number. And then 273 divided by 298. So that's 0.916. So now I just multiply all of them. So 250 times 0.961 is that, times 0.916 is that, 220. And we are talking about volume in cubic centimeters, I believe, right? So there's your answer. So that's a different method, factor method, just looking at the relationships, looking at the ratios, changing everything the same. All right.